Life cycle of a star. As we look at our sun and other stars in the night sky, we wonder to ourselves, where did our sun come from? Where did all of those stars come from? All stars started in a nebula. A nebula is a giant area of dust and gas. This dust and gas is being brought together through gravitational pull. More and more of this dust and gas is brought together, and eventually the dust and gas is turned into a protostar. The protostar is not a true star yet. During the protostar phase of a star's life, material is being brought together through gravitational pull. Gas and dust from the nebula is all being brought to a center location. As this dust and gas is being brought to that center location, lots of pressure is occurring. That pressure causes things to heat up. As things begin to heat, the protostar begins to glow. It's a very dim glow, but what you're actually seeing is the heat and light being given off by a protostar. Also during this time frame, material starts all going in one location. It is the beginning of the orbital paths of stars and meteorites and other objects that will go around the future star. After a star has gone through its protostar and finally has brought all the matter together, hydrogen to helium fusion starts taking place. This hydrogen to helium fusion is where we start saying this star is truly a real star, and it goes through its main sequence phase. During its main sequence, the star is going to take hydrogen atoms and fuse them to form atoms of helium. Now, this is not chemical bonding. It is not hydrogen and oxygen turning into water. It is the true formation of one type of atom turning into a different type of atom, hydrogen turning into helium. During this process of hydrogen to helium fusion, small amounts of matter are turned into energy. This energy is why stars are hot and bright, is that energy that's being given off. The size of the star, or the amount of matter in the star, controls how much fusion is occurring. So in a red dwarf, it does not have as much matter, so therefore it does not have as much gravitational pull. Because there is less gravitational pull, there is not as much fusion occurring. In our star, our sun, there is more fusion occurring than in a red dwarf. It is still not as much as in a blue-white supergiant. Because the blue-white supergiant is so massive, so large, that they have a lot more gravitational pull, therefore a lot more fusion occurring. The amount of fusion that is occurring in the star controls the actual temperature of the star. Because the red dwarf is smaller, it does not have as much fusion, therefore it's not going to be as hot. A blue-white supergiant has a lot of fusion occurring, therefore it's going to be a hotter type star. We can see this when we're looking at stars because a red dwarf has a red color. The red color shows that the star is a cooler type star. Our sun is a medium-sized yellow star, while there are other supergiant or giant blue-white stars out there, the blue-white being a hotter type of star. Think about when you're actually looking at a flame. In the center of that flame, there's always that blue part in there. That's the hottest part of the flame. We sometimes think that red is hot, even when we're looking at taps and things like that, when we're doing with our water. But a true hot color is a blue-white, and red is going to be the cooler part. In addition, the size also controls the lifespan of the star. Because the red dwarf is so much smaller, has less fusion occurring, it will take its amount of matter and it's going to last for a very long time. Some people think that red dwarfs will last up to 50 billion years. Our sun's lifespan is about 10 billion years. We're going to go through our fuel source quicker than a red dwarf, but not as quick as a blue-white supergiant. Some of those blue-white supergiants may only last for 50 million years or so. They burn through their fuel very, very quickly. Eventually, the main sequence star runs out of fuel. As the hydrogen can no longer turn to helium, the star begins to shrink for a small period of time. This allows the star to increase the gravitational pull in a small area, and it becomes hotter and more pressure on the core of the star. As this starts occurring, eventually the helium has enough force to start turning into larger elements, elements such as carbon. As the helium turns into carbon, the star gains tremendous amounts of energy. And in that core, the outer layers are forced then blown off the outside of the star. As these outside layers are blown off the outside of the star grows to a giant size. As you can see in this picture right here, the sun is going to go from its size it is right now, and you can see that in the bottom part of the diagram, to a star that is tremendous in size. The sun is going to grow to where the outside layers of the sun will be almost touching where the Earth is right now. Huge amounts of size. The color of the star becomes red. You'd think because the star itself is fusing helium into carbon, it's going to become hotter. Well, the inside core will become hotter, but that energy has to travel much, much further. And by the time the energy has got to the outside layers of the star, it has now become cool. And the star goes from its original color to a red in color because it is cooling down. As red giants continue the outside expansion of their gases, they continue to float away if that original star, was a small or medium-sized star. As those gases keep floating away, a planetary nebula is formed. A planetary nebula gets its name because a long time ago, when scientists were first looking at these through telescopes, they thought this was more of a planet around a star. And it's got its name from that. There are actually no planets in a planetary nebula. It is just the gases that have been blown off. In a larger size star, it will not have a planetary nebula because those gases are going to be brought back in because they have enough gravitational pull. After the gases and dust have eventually been blown off, what is left over is the original core of the star. You can see in this picture here what our sun will eventually turn into, a much smaller star. The white dwarf gets its name because it is white in color, sometimes blue depending on if it's a little bit larger, and a dwarf because it is a small star. It is white because it is very, very hot. The heat comes from the fusion that is occurring. It is helium to carbon fusion, and because you have that fusion occurring and the star is very, very small, you have a tremendous hot area and the energy does not have very far to go to. Therefore, the outside layers are very, very hot. So let's put this all together. For our star, which is a medium-sized star, and also for small stars, this is going to be the general life cycle of the star. It starts off as a nebula, and from a nebula turns into a protostar. The next, for our star, 8 to 10 billion years, is going to be in a main sequence star. It goes through that phase, turning hydrogen into helium. Then it shrinks for a second and turns into a red giant. Because the gravitational pull is not strong enough to pull those outer layers back in, those layers drift off. That's the planetary nebula phase, and eventually keep on drifting off. All that's left over is just the core of the star, that white dwarf. The white dwarf is going to be hot and small. But this doesn't occur for all stars. Our large stars have enough gravitational pull to bring back the red giant material. So as they go into a red giant, they actually turn into a super red giant. Here's the size of our star when it turns into a red giant. But take a look at what some of our super red giants are. Much, much larger. You can see in this diagram the Earth's orbit, which really is how big our star will get to when it turns into the red giant phase. It is almost not even anywhere close to the size of a super red giant star. There's enough gravitational pull to bring all that material back down to a center location again. And as it does that, there's enough energy to turn the carbon and start fusing it into even larger materials, iron, uranium, metals that are very high on our scale. Depending on how much mass is left over after the supernova phase, you have a black hole or a neutron star. A neutron star is made of primarily neutrons. They are detected because they eject energy from its polar regions. And a black hole is a point in space where no other matter can escape. We can't see them because they suck in even light. If the star is 1.5 to 9 times larger than the sun, the core will go into that supernova, and then from the supernova into the neutron star. If the original star was 9 times larger than the sun, then it's going to collapse all the way back down into a black hole. Here's another diagram of a life cycle of a star. It starts on the left-hand side, and you can see how it goes into a nebula, a protostar. If it's too small, it actually will turn into a brown dwarf and never get into the main sequence. From main sequence, it goes into a red giant. If it is a smaller or a medium-sized star, it goes from red giant to white dwarf, and eventually to a black dwarf when there's no more helium to fuse into carbon. If the star is larger, it takes all the material, sucks it back in, and explodes into a supernova. That supernova then turns into a neutron star and or black hole, depending on the amount of matter that's left over. Here's another diagram. And again, it's not important that you memorize all of these, but know how you can look at the diagrams and see how they work. Again, in the middle of this one, you have the nebula. The nebula goes into a mid-sized star or a massive star. From there into the red giant phase, planetary nebula, supernova. You have a white dwarf, you have a black hole, you have the neutron star. But look at all that extra material. The leftover debris from the supernova that's blown off goes back into nebulas. The planetary nebula material that's been blown off, again, goes back into nebulas. All stars follow this type of life cycle, and it all depends on the size of the star, the original size, what will occur with the star itself.